All right, IBAASL1 kids. Today we're going to go a little bit deeper with logarithms, and we're going to start with some examples of how you can break apart and smash together logarithms. Then after that, we're going to talk a little bit like a change of base rule, and then we're going to talk about solving logarithmic equations. So with this problem, they tell us if x equals log 2 and y equals log 6. So they're giving us these little building blocks, and then they ask us to write each expression in terms of x and y. Now, you might notice that 12 is not a log 2 or a log 6, but what you can do is rewrite 12 in terms of 2's and 6's. So you can rewrite this as 2 times 6. Then, using your log properties or log laws, and multiplication inside the argument can be broken apart into addition. So this becomes log 2 plus log 6. Then log 2 is x and log 6 is y. So we can replace this with x and this with y. So our final answer here is just x plus y. Log 3 is slightly trickier because you're like, well, how do I break that apart into 6's and 2's? Recognize that 6 divided by 2 is 3. So you kind of have to like look at it and like try some things and decide if you can figure out a way to use 6's and 2's to get a 3 out of it. So this is 6 over 2. Then any division inside a log argument can be broken apart into subtraction. So this becomes log 6 minus log 2. And then that becomes log 6 is the same thing as y. And log 2 is the same thing as x. Now, for log 48, it's a little bit trickier. The first step is you can break this apart. You can get a 6 out of it. You can do 6 times 8 to get 48. So you can break that apart into log 6 plus log 8. But then you might look at log 8 and be like, how do I write that in terms of 2's and 6's? Well, it's a little bit tricky, but 8 is a power of 2. You can rewrite this as 2 cubed. Then there's that property of logs where a power out on an argument can go out in front and become a multiplier. So this becomes log 6 plus 3 log 2. Then the log 6 is y and the log 2 is x. So our final answer here is going to be y plus 3x. And that's that. Very similar to the last problem. We're going to let x equal log base 3 of p and y equals log base 3 of q and z equals log base 3 of r. Write each in terms of x, y, and z. Well, the first thing I'm going to do is I'm going to take everything inside the argument and try to break it apart into separate logs. So the division can get broken apart into subtraction. So log base 3 of pq minus log base 3 of r. Then the p and q multiplication can be broken apart into addition. So we get log base 3 of p plus log base 3 of q minus log base 3 of r. Then you have it in terms of log base 3 of p, log base 3 of q, and log base 3 of r. So the p is x, the q is y, and the r is z. So this is minus z. And then you are done. Same thing over here. I'm just going to start breaking apart things. Like the first thing is I'll handle the subtraction, the division that turns into subtraction. So we get log base 3 of p squared r minus log base 3 of q cubed. Then I'll take the multiplication in here and break it apart into log base 3 of p squared plus log base 3 of r minus log base 3 of q cubed. Then I will take those powers up top and move them out front as multipliers. So this becomes 2 log base 3 of p plus log base 3r minus 3 log base 3 q. Then I can replace p, r, and q with those letters that they're equal to. So p is x, so this becomes 2x. R is z, so this is plus z, and then minus 3y. Yep, and then we're done. Okay, there's a couple of specific logarithms that we haven't talked about yet. If you have a log base e, now last class we sort of, I guess I missed it in the video, but e is just a number. It's like pi, it's an irrational number. It's about 2.718. Now, you don't ever need to really know that. There's a button for it on your calculator. I want you guys to know, if you have log base e, this is the same thing as ln. This is called natural log of x. So ln x is the same thing as log base e. We just never write it like that. We always just write ln of x. Very similarly, there's a thing called a common log, where if you have a log base 10, mathematicians would never write log base 10. You can just write log on its own. If you write log on its own, it's implied that the base is 10. So this is the common log. The good news for you guys is that all the properties of logs, all the laws, work the exact same way with any log. So like natural logs, common logs, log base 5, log base 100, they're all the same thing. All the laws work the exact same way. So for this first problem, we're going to find the exact values. The first thing I'm going to do is take this 2 and move it out front. So this becomes 2 natural log of e. Now, if you think about the natural log of e, if you do like a little spiral off to the side, that's basically like log base e of e is equal to what? Well, if you do like a quick spiral and say e to the power of this equals this, you can quickly see that log base e is equal to 1. Which means that this is 1. Which means the whole thing is 2. Here, this is that special scenario that I showed you guys last time, where you can think of it like this, that it's e to the log base e of 5, which is what a natural log is. And then when this number and this number match, you can just get rid of them and say that they're equal to the argument. So that one is just 5. On this one, we're going to break apart the division into subtraction. So we get ln e to the x minus ln e to the y. And then you can bring those x's and y's out in front to get x ln e minus y ln e. And then we established in part A that ln e and ln e are both just 1. So this becomes x minus y. That's the exact value. Now, the change of base formula. The change of base formula states that if you have log base A of x, that you can break this apart into 2 logs being divided. So the 2 logs being divided are going to be log of x in the top and log of a in the bottom. Now the base on this one can be anything we want it to be. So this is where a, b, x are all greater than 0. These are all positive numbers. But the cool thing about the change of base formula is that you can change it to any base that you want. The main reason people use change of base formula a lot of times you'll encounter a problem where you're trying to find the exact value of a certain log and you need to use the change of base formula. If it's in a base that's not nice, like a common log or a natural log, you can use the change of base formula to turn it into common logs or natural logs. But technically you can change the bases to anything you want. An example of this, find the approximate value of log base 3 of 20 using common logs. Well, if I don't use common logs right off the bat, common logs and then natural logs, if we just think about spiraling, so log base 3 of 20 is the same thing as 3 to the what equals 20. So that's when you could pull out your calculator and say, okay, 3 to the 1 is 3, so it's not that. And then you could say 3 squared is 9, it's not that. And then 3 cubed is 27. So then you can say, well, 2 was too small and 3 was too big, so it's like between 2 and 3. So then for all you guess and checkers, you could do like 2.5 and see how close that is, and then 2.25 or something like that to figure out like where that number is. The better way to do this problem is to use the change of base formula. So log 3 of 20 can be broken apart into common log 20 over, that's a terrible line, common log 3. So this is using common logs. Then in your calculator, you can punch in log base 20 or log 20. Let me do it real quick. Divided by log 3, and you get 2.73. So that is your answer, that log base 3 of 20, the decimal approximation is 2.73. Now that's using common logs, but the change of base formula, you could have used natural logs. You can change the base to whatever you want. So this could be ln 20 over ln 3. And then when you punch that into your calculator, you are going to get the exact same thing. So it doesn't matter whether or not you use common logs or natural logs. They're both the same thing, 2.73. And then on your calculator, you could try 3 to the 2.73 and see what this equals. So 3 to the 2.73 is like 20.07. So it's not an exact science because we're rounding a decimal, but like to 2 decimal places, 2.73 is the approximation. Now, let's actually start solving things with logs. You guys, there's no nice power of 2 that gives us 10, because 2 squared is 4, 2 to the third is 8, and 2 to the fourth is 16. So it's somewhere in between 3 and 4. Here's how you use logs to solve this. You log both sides. Then you use that power property to bring this guy out in front and say this is x log 2 is equal to log 10. Then you divide with both sides by log 10 to get log 2 to get log 10 divided by log 2. Now, this is the exact answer. If your book wants a decimal equivalent, this is about 3.32, which we knew it was in between 3 and 4. So this is a decimal approximation. Next problem, similar process. take the log of both sides. The reason you're taking the log of both sides is to get that x out of the power spot. That's what's a bummer about solving these, is you need the x to be like a big multiplier, not a power. So we'll log both sides to get log 3 to the 2x equals log 20. Notice that I'm using common logs for all this. Like, you could do different bases, but who cares? You're going to use common log button on your calculator anyway. Then the 2x comes out in front. And then we divide by log 3, so we get 2x is equal to log 20 over log 3. And then we can divide both sides by 2, which is kind of the same thing as multiplying by a half. So we get x is equal to log 20 over 2 log 3. Now, once again, that is the exact answer. Oh, they use natural logs in the book. Weird. So you could just leave it here, or you could do the decimal approximation, which is 1.36, using your calculator. Next up, same process. Log both sides. Bring the power out in front. So you get 1 minus 2x times log 5 is equal to log 50. Divide both sides by log 5. So we get 1 minus 2x is equal to log 50 over log 5. Subtract 1 from both sides. And then divide everything by -2. That's kind of a bummer. That doesn't work out nicely. Oh, they just multiply by a negative half in the book. Sure, I can do that. So that is your exact answer, but it is about -0.715. All right, last example, or no, wait, 2 more, sorry. Last example, a little bit of a doozy. We're gonna take the log of both sides. Then there's multiplication inside both of these, so I'm gonna break those apart into addition. Then those x's in the power spots are going to come out and be multipliers. Then anything with an x, I'm going to move to one side, and anything without an x, I'm going to move to the other side. So this guy, I'm going to kick over here, and then this guy, I'm going to move over to this side. So we get x log 3 minus x log 2 is equal to log 5 minus log 2. Just making sure I did that right. Yeah. The reason I did that move is now both of these things on the side have an x in them. So I'm going to factor out that x and get x times log 3 minus log 2 is equal to log 5 minus log 2. And then you can divide both sides by this whole parentheses here and get log 5 minus log 2 all over log 3 minus log 2. So that would be your exact answer, and then the decimal approximation would be 2.26. So there's the whole problem. Ooh, last one, and it's kind of a sneaky one. The way you need to think of this first nomial right here is that this is e to the x squared. And then the rest of it we can just write like normal. Now, the reason that we rewrite it is that this is a sneaky quadratic. It's very similar to x squared minus 3x plus 2 is equal to 0, which you can factor into x minus 2 and x minus 1, and then set them equal to 0. So over here, it's the same thing, because when you square ex, you get e to the 2x. So this factors into e to the x minus 2 and e to the x minus 1. Then you have to set these both equal to 0, like you would normally solve a quadratic, and say e to the x minus 2 is equal to 0, e to the x minus 1 is equal to 0. Then you add 2 to both sides here. I'll just work both of them at the same time. And then you're going to have to natural log both sides. Is that the way we should think of this? Sure. Yeah, if I take the natural log here, we get natural log of e to the x equals natural log of 2. Then the x comes out in front, and we get x natural log e is equal to ln of 2. And then natural log of e is just 1, so this is x is equal to the natural log of 2. Here, if I natural log both sides, we get natural log of e to the x is equal to the natural log of 1. And then I just showed that this side is going to be x is equal to ln of 1. But then if you think about ln of 1, if you do a little sidebar, that means log of e of 1 is equal to something. And if you spiral that, oh my gosh, spiral that, that means that that has to be 0. So x is equal to 0. And these are your two answers. All right, you guys, we made it. Please ask me questions.